Good morning. Now we are going to see the fundamentals of robotic system. So this subject it is giving a overview of what it is available in the robotics fundamentals and other things. Uh, so this unit 1 consists of introduction to robotics, history and development in robotics and its robot autonomy, definitions and law of robotics. And next we will be seeing the terminology of robotics and accuracy and repeatability, dexterity and compliance. And RCC device of the robotic simple problems you will be going to see it. Then specification of robot, speed of robot and robot joint and its links, and robot drive systems, hydraulics, pneumatic and electrical systems, then mechanical gripper, slide crank mechanism and screw type, and rotary actuator, cam and magnetic gripper and vacuum grippers, and gripping force analysis and gripper selection and design. And if you look at the definition of RIA, see everyone is thinking about the robot means they are having their own definitions, right? Most of them we are comfortable with seeing the films and seeing that a humanoid robot is the only one is a robot, but it is not so. So they have developed a standard Robot Institute of America. They come up with a standard definition. The definition is a reprogrammable, multifunctional manipulator designed to move material, parts, tools or specialized devices through various programmed motion for the performance of various tasks. So this is the definition. So if you look at the robot should be a reprogrammable one. It should not be fixed one, and it should have a multifunctional one. Okay, it should have a multifunctional manipulator. Manipulator means nothing but where you are going to give the end one, gripper. Okay, and manipulator move the material. It can move the material or parts or tool. It can do the not only the pick and place operation, it can do a welding also. It can do any number. Nowadays they are doing with the surgery and other things. So the manipulator, at the end of the manipulator, they'll be fixing it and they'll be doing it. And the specialized device, various programmable one. So it can be done with a various options. So if you look at the standard definition of a ISO, a automatically controlled, reprogrammable, multi-purpose manipulator programmable in 3 or more axes, which can be either fixed in place or mobile for the use of industrial automation application. So the definition which is given by International Organization of Standardization, they given it should be automatically controlled. So the robot should be automatically, not the manual one, and reprogrammable as given the previous one. It should be a reprogrammable and multi-purpose. So it should be a multi-purpose manipulator. So the end effector should not be fixed for particular application. It should be a multi-purpose and it can have a 3 or more axis. So the basic one is a 3 axis one, and which can be either fixed in a place. So the robot can be fixed at a single location, or it can move to the required location in the industrial automation and it can perform the operation. So if you look at the to qualify as a robot, so the robot should sense and perception. So sense means it's getting some information and perception means doing some work. Okay, so sensing some information and converting the information into a useful part and carry out the different task. So it should be carry out the different task means locomotion or manipulation, do something physical such as moves the manipulator object. So after sensing the one, it has to do some work. So if you look at that industrial robot, so we have to identify whether the object is there or not. Once it is identifying the object is there or not, then it has to go to the required location and carry out the desired operation. Okay, then reprogrammable. So it should not be fixed for a one. See, the robot is mainly used for reprogrammable. See, whatever the configuration or whatever the location, it has to do it the proper one and function autonomously or interact with the surround. So it should be function autonomously. Autonomously means automatically it has to carry out the function. So what are the 3 laws? So as far as the robot is concerned, it should have some laws. It should obey the laws. Then only because the robot is the one previously it is called as a slave. So the slave should not take on its own decision. So it has to follow some laws like a human being. So first law is stating that do not harm the human being. So whatever the machine, whatever the robot which we are developing it, it should not harm the human being. It is only for to serve the human being, not the harm the human being. So the robot must not harm a human being or through inaction allow a human being to come to harm. See, the robot, suppose if it is not an active position, even though it should not harm the human being, and suppose if it is an action, that is also you should not harm the human being. So the robot should not harm the human being. That is the first law. The second law says that obey the human being. See, as a if it's a master and slave, whatever the master says the word, the servant or slave has to obey it without asking why I have to do it. So that is the fundamental of second law. So if you look at the second law, a robot must always obey the orders given by it by a human being, except where such order would conflict with the first law. See, if a human being is telling, come and hit me, you should not hit. Okay? The main purpose is it should not harm the human being. It should obey the human being, but it should not harm the human being. So that is a very, very important. So don't think that if it is giving an instruction, go and hit that person, you should not hit. It should not harm the human being. Okay? So that is the main purpose of devising the robotics. So it is violating the first law. So it should not harm the human being, but it should obey it, but it should not harm the human being. So if you look at the third law, protect itself from the harm. So the robot must protect its own existence as long as such as protection does not conflict with the first and second law. So if you are thinking that the robot want to protect its same robot, while it's protecting it, it should not harm the human being. Okay, it should not harm the human being. So it should be inactive. If it is coming and touching it, the robot should be stopped. So that is the one. So if you look at the three laws, the first law says do not harm the human being. So if you look at in red color, the fonts are given, do not harm the human being. The second law, obey the human being. And third law, protect itself from the harm. So if you look at all three laws, it is only meant for the human being. Okay, human being should not be affected by the robotics. Okay, that is the main aim, and it should serve the purpose of the required one. And if you look at the component of the robotic system, so robotic system will have one controller and drive unit, and you will have one base and link or arm, and you will have the link will be connected to the base with the help of the joint, and similarly these two are linked connected by a joint, and here also link or arm and connected by another link by a joint. And you will have a one wrist, that is the end effector. So the end effector, whatever the purpose you want to use it, that will be using for it. So if you look at this robotics one, so you will have a controller. Controller is the one, it's controlling all operations. See, if you want to write a code, after writing a code, the all robot, it is done only with a electrical motors. Okay, servo motor or stepper motor, it will run. So whatever the codes we are giving it, it should be converted into a electrical pulses. So that electrical pulses will be generated by this controller. So once it is giving a controller, that electrical signal should be given to the robot through drive unit, because each one we have to give a proper servo means servo driver unit you have to give, stepper means stepper driver unit you have to give. So it should have a driver unit to convert the electrical signal, electrical voltage to a understandable one to the robot. Okay, so that it will do the necessary operation. So this component, if you look at it, so you will have one controller and driver unit, and this is the component of the robot, and here we are going to use the end effector to doing the useful operations. So this is the one which we are having in our lab. So this is the same one which is given here. So this is the controller, and this is the where you will be. This is called as a teach pendant, where we are going to write the program and other things. And here you have a step servo motors are placed here. So individual 6 axis you will have a servo motor, and this is the end effector where the gripper is placed. Okay. So this is the 6 axis robot. Each axis, the base one you will have a 3 axis, and first primary axis is a 3 axis, and secondary axis as a 3 axis, totally 6 axis. So it can do the required performance. So if you look at the one, and this is the parallel manipulator. So if you look at the that is called serial manipulator. This is the parallel manipulator. So you will have a arms, and this is the vacuum gripper which we are having it. This is the vision based robot where whatever the symbols say ABB or SRM or whatever the one mechanical or any one which is engraved it, here the camera is available where it will capture the image, and the runwayer will run the path. So while it is coming it out, so this vacuum gripper will pick it up, and this is the pallet which is carrying it. So it will place it to the required position as we programmed it. So here also you can look into it. This is the teach pendant, and then this is the controller. Okay. So this is the high speed robot, and you will have a lighting option, and you will have another switch, and other options are available here. And if you look at the robot autonomy, so if you look at the robot autonomy, the manipulator consists of a joints and links, and joints provide the relative motion. So each joint it provides the relative motion one to another one. So it can be a turning pair, or it can be a screw pair, or it can be a spherical pair. So it will convert the relative motion. Links are rigid members between the joints. So links usually will not have a movement. A few flexible links are available that it can have that it can change the shape. Otherwise links will be having rigid members, and various steps on it can be linear or rotary. So links can be linear movement it can give, or rotation movement also it can give. Each joint provides a degrees of freedom. So degrees of freedom is nothing but what how much it can move. Okay. The robot one possesses the fixed 5 or 6 degrees of freedom. So it can move at 6 different actions. So 6 different movement it can have it, or 5 degrees of freedom. And manipulator consists of two sessions. One is the body and arm, positioning the object in the robot work volume. Okay. Or wrist assembly, where orientation of the object. So we'll primarily I told that it is having a two different axes. One is called primary axis, another one is called a secondary axis. The primary axis requires to the go to the required location, and secondary axis go to perform one is doing the useful operations. Okay. The wrist one it consists of a where you are going to give the end effector and other things. And if you look at the same one which is available here also, so the base one, this is the base one, and you will have a link. So this is the link which you are having it, and you are having a joint is a turning per joint 1, and you are having another link and joint 2, and you have another link joint link 3, and end effector end arm, where you are having the end effector, the components are produced. So this is the typical jointed arm configuration robot. Okay. And now we'll go to the what is by degrees of freedom. See, each one is having a degrees of freedom. What is the clear definition of degrees of freedom? Degrees of freedom is defined as one of the variable required to define the motion of the body in the space. So the degrees of freedom in a system depends upon the number of variable or coordinates that are needed to describe in its position. So each joint in a robotic systems gives the robot 1 degrees of freedom. So each joint, so depending upon the each joint is depending upon the one. If it is a turning pair, it can give a 1 degree. If it is a spherical pair, it can give a 3 degrees of freedom also. So the say X, Y, Z, where it can move. Okay. Suppose if you are having a 1 degrees of freedom turning pair, it can move in a X direction only, means it is a degrees of freedom is 1. So it can move X, Y, and Z, means it has a 3 degrees of freedom. Okay. So the movement in the simple words, if you are telling it, it is a movement. And the robot joint is a mechanism that permits the relative motion between the parts of the robotic arm. So it has to, while suppose see always I told that the stepper motor or servo motor is connecting at the end, when you are giving a signal, it has to process to the end effector where it has to move it. So the mechanism should put the relative motion between the one. And the joints of the robot designed to enable the robot move its end effector along the path one position to other desired one. So joint has to go to the required location where to do the operations. And if you look at the prismatic joint, so also it's known as a sliding as well as one. So prismatic is a linear joint. They are called the prismatic joint. Because the cross section of the prismatic joint is a generalized prism, permits link to move in a linear relation. So if you want to move it in a linear one, so you will be using a prismatic. Prismatic means a square or rectangular. In a cross section wise, it is in a square or rectangular, so that the rotation motion will be arrested. Okay. So that joint is usually it's called a prismatic joint. And revolute joint. Revolute joint, angular motions will be given. So it have a three types. One is a rotational joint, and another is a twisting joint, and the revolving joint. So the revolute joint permits three type of angular motions. One is rotational joint, another one is twisting joint, another one is a revolving joint. So it will permit the so now if you look at the one, so here the prismatic joint, it's a linear one, it can move up and down, and flexible beam, and this is the revolute joint, so it can move up and down here. Okay, the turning axis, and you are having a torque provided here. And mechanical joint of some translation motion prismatic, so linear joint, so it's the notation, it is given as L. Orthogonal joint type, it is given as a O. Orthogonal means perpendicular. And rotary motion revolute joint type R, or twisting joint type T, and revolving joint type notation as a V. So these are the one mechanical joints of the robot. And linear one, so if you look at the linear one, so the input link, when you are giving input, the joint motion will be in a linear one. Okay, this type is a linear one, it's a relative motion between the input link and the output link in a translation sliding action with the axis of the two links parallel. So this link and these links are parallel to each other, and when you are giving a input link, it has to move in the forward direction, or like transverse or forward direction, like this. The arrow cut, it's indicating where to move. And if you look at the orthogonal one, so if when you are giving a rotation here, the output one should be orthogonal. This is the input one, blue color indicating the input one, and yellow color indicating the output one. So it has to do in a perpendicular one. Okay, this is a perpendicular one. So this is the orthogonal type. So if you look at the definition, the relative movement between the input link and the output link is a translation sliding motion, but the output link is perpendicular to the input link. So if you look at here, the input link, if you are giving the input link, the output link is a perpendicular one and rotational one. So now we will look at the rotational one, the typically rotated as R. So the input link, when the joint motions are up and down. So here the translation. So this is the hinge like arrangement where we are seeing in a row. So like typical example is doors. Doors will have a hinge to fit it out. So if you remember that the doors, this is a joint motion where it's having a motion. This arrow gets indicating how it will move. When you are giving a one, this is the joint. When you are giving a link, how it can move. So this is the rotational joint. And twisting joint. The twisting joint is nothing but when you are giving a one, it will twist. So if you look at the rotational joint, it is up and down, just like an arm, how we are moving it out. And twisting joint, just like a wrist, how we are moving it out. So these input layer, output layers are parallel to each other. See, the parallel to each other, but it will twist. It will twist. Okay. So the motion will be in a twist. So this joint is rotated as a T. And revolving joint. Revolving joint is rotated as a V. So if you look at the output link, the joint motions, it is a perpendicular, say input and perpendicular, but it revolve around this joint. Okay, revolve around this joint. So this joint is nothing but a revolving joint, and it is notated as a V. Now, what do you mean by constraints? So constraints, suppose if you look at this diagram, so this object, it is connected with this one. Will it rotate? it cannot be rotated because it is in a trapezium shape. It will not allow to rotate, but it can allow to move in a only one direction. So we are constraining all the direction except linear one. Okay, so the linear one, it is nothing but movement. Now if you look at here, this joint can move it rotate because it is a cylindrical one. Here it is a trapezium one, but here it is a cylindrical one, so that this connected component can rotate about it. Okay, it's a rotational constraint, and it can move also, both it can be linear as well as rotation. And if you look at the degrees of freedom, how it can be notation can be given. So the link between this, it's called a dj, and this is the link that is given as jk. A of jk is a unit vector, the angle how it is rotating it out, and joint axis rotation 1 and link. So 1 degrees of freedom means 1 is a revolute joint. So if you look at here, this is the revolute joint, 1 degrees of freedom it is rotating. Then here we are 1 is a prismatic joint, where we are having this movement in the prismatic joint. Okay, prismatic joint. And now we are look at the joint with a 2 degrees of freedom. So it can move it in a rotational wise as well as linear wise. So two movements are possible. So that is called 2 degrees of freedom, the cylindrical joint. And if you look at this joint, it is a 2 degrees of hook joint 1, where it can move about here as well as here. Okay, and this joint is a ball joint. It can move a ball type of arrangement. It can move in a x, y and z direction. So 3 degrees of freedom is possible. Okay, 3 degrees of freedom is a ball and jocket joint. This is the hook joint, and this is the cylindrical joint. Okay, now if you look at the cross section wise, this is the revolute joint, where it can rotate. Okay, this is the component where it can, this is the outer body, the green color one. And prismatic one, if you look at it, it is in a rectangular shape, it is available. Here the movements are given, it can move it in a linear direction. And screw type, if you look at the screw type, due to the screwing action, this component will be move up as linear direction. Okay, and this is also 1 degrees of freedom, because while giving a rotation movement, it can move in a linear direction alone. In the cylindrical one, if you look at this component, so while giving a rotation, it can move up and down. This portion can move up and down, as well as it can rotate also. So 2 degrees of freedom cylindrical. And spherical means it can rotate. This component can rotate x, y and z. 3 axes it can rotate. So it is a spherical component. And planar means, so it is a 3 degrees of freedom. This component can rotate. So this component rotate about the base, and it can move it in the linear ways also. It can move it in the x and y direction, and as well as this lateral direction. So 3 degrees of freedom. So if from this diagram you can understand how it can move. Accordingly, the degrees of freedom is defined. Okay. So lower kinematic pair. The lower kinematic pair, which is the one, suppose if you are rotating here, this is the one is the theta degree. So these two are joined here. So this is the pin diagram where this component is connected to this component, the rotation action is taking place. Okay. So this is the cylindrical component, and the movement also rotation as well as 1, and prismatic component rotation 1 it is given, and the spherical component where it can move it into 1, and planar movement x, y and theta. So now we can have an idea how to identify number of joints. Okay, number of joints and how it can be. See, look at here. If you this is the typical workspace of one. You want to do a measuring a ceiling head. This is the one you want to do an operation. The robot has to move it along this direction. Okay, so what are the ways it can move? While giving a direction, this platform can move it in the linear one. So 1 degrees of freedom, and this component can move it here. Okay, so 2 degrees of freedom. This component can move it from an up and down. So 3 degrees of freedom. Okay, so this is how you have to find it out which is the joint and which is the degrees of freedom. So further it can be converted into a point in 2D, point in 3D space, rigid body in 3D space, spatial manipulator, parallel manipulator. So point in 2D is at 2 degrees of freedom, point in 3D is at 3 degrees of freedom, rigid body in 3D, if you look at the 3D, it will have a 6 degrees of freedom, spatial manipulator will have a 6 degrees of freedom, and planar manipulator will have a 3 degrees of freedom. Thank you.